Hello, everyone.
Hello.
Hello.
Hey, so let's get started. Um, so, for the last couple of years at Unity, we've been working on rebuilding the core of Unity, and we've been calling it the DOTS tech stack, the data-oriented technology stack. And I want to give you an overview of what we're doing and why we're doing that. So, we have a couple of principles around which we are rebuilding the core of Unity. And the most important one, I think, is what we call performance by default. And performance by default, for us, what it means is really taking advantage of the hardware that exists. And I think that today, most games don't actually take advantage of the hardware that exists as it is today. When you look at this today, in the last 10 years, one thing that you can see is that processors don't just get the single core performance of processors, the frequency, the megahertz of the CPU doesn't get any faster. It's essentially been flattening out. But at the same time, what we do get more of is we're getting more and more cores. Now, in almost every mobile device, you have around 4 cores or more. On consoles, you have 6, 8 cores. And PCs these days have up to 16 cores. So it's really not possible for us to say anymore that we write performant code if we're not actually taking advantage of all these cores. If we could get these 16x speedups by just writing multi-threaded code, we're not doing that. We're in fact not writing performant code. And in the same way, one way in which computers have been getting faster is SIMD instructions, specialized instructions that... Actually, can you hear me properly with this?
Yeah.
Okay. Specialized instructions which really make it so that you can process you have a single instruction and it processes multiple pieces of data at the same time. But both of these technologies are difficult to leverage and difficult to use in a game. So what we're doing with DOTS is really focused on 3 core parts of the engine. The first one is the C# job system. The C# job system is all about taking advantage of the multi-core hardware. So it's about making it easy to write multi-threaded code. Because in fact, writing multi-threaded code is difficult. How many of you have written multi-threaded code in a game before? Cool. Okay, how many of you have nightmares about the time where you get a race condition that can only reproduce on your client's, on some random computer, and you just can't reproduce it, and then they get a crash, or maybe the night before some QA guy can reproduce it? That is a nightmare scenario. And that is what makes writing multi-threaded code the thing that most game developers don't actually do. So we invested a lot of time and effort into making it safe. So with the C# job system, we have a safety system that automatically detects any possible race conditions that you might create in your code, and it tells you about them immediately when you write that code, and it tells you where that race condition is and how you can fix it in an actionable error message. So, because at the end of the day, I think if we want to get to a new level of performance, it has to be easy to do it. If it's difficult to write multi-threaded code, few people will do it. And that's the point of performance by default. They want to make it easy. The second part is the burst compiler. The burst compiler takes advantage of that same code that you can write in the C# job system. And it's a specialized compiler It takes C# code and outputs highly optimized machine code. And it takes advantage of the SIMD instructions in the hardware and automatically generates vectorized code for you so that you can get the best possible performance. And the last part of getting great performance is data layout. So the entity component system lets us lay out data in a way that is completely linear to how you're accessing it at runtime. And that's super important for performance, because these days, almost everything that you do on a computer is bandwidth limited. So let's take a look. At a demo. This is a demo that we did with our friends at Naudius. We showed that the first time a couple 1.5 years ago. And in this demo, you can see we have a massive amount of units on the screen, right? So let me zoom in here. There are 40,000 separate units. They are all individually animated, and they have their own logic that makes them fight with the enemy. So this is really a stress test of the entity component system. And I can we can blow up all of these units here. And what's happening is this is not a specialized system that somehow deals with a massive amount of entities being created and destroyed. This is just totally normal entity component system code, and it just scales. You can instantiate a massive amount of entities. Here you have these arrows, how they move, how they try to shoot arrows at each other, the animations being animated. All of these things are fully multi-threaded. And on this computer, it's a laptop. There are 6 cores in it, so that there are 10 logical cores that we can use across which we spread all of these jobs. And that's really the thing, right? This is where you can get a 10x speed up on a modern PC if you just actually take advantage of the hardware. Then we also have the burst compiler. All of these jobs that you saw are running in our burst compiler, and that means we get highly off-vectorized code, and generally we get on the order of 5 to 10x speedups with this technique. And lastly, all the memory is laid out in exactly the order in which these components process them. And so combined with this tech, we can get something on the order of 100x speedups, overwriting normal mono-behavior code as you would be used to from Unity. So that's the kind of speedups that you can get if you're willing to rethink a little bit about how you write your code. So let's take a look at what that really means. When you have game objects, you basically have game objects are a container. There are position components, rotation component, rigid bodies, all these different components that work together to make the behavior of your game. And these are allocated randomly in memory. In the entity component system, this is different. In the entity component system, an entity is simply an ID. It's like a database. It's a database of positions, rotation values, renderer components, rigid bodies, whatever you need. And we automatically lay out that data in the order that it's processed at runtime. So we're going from this to something like this. So when we're processing our data, we want to process, for example, a bunch of entities that have a position component and a rigid body component. And everything is grouped together automatically. Similar components are grouped together automatically in what we call chunks. And what that means is that when we run a system code, if we want to process the data, it's linearly laid out. We only load into memory the data that's actually necessary. We don't waste any performance on loading data into cache lines that are not actually used at all. So the way that works is every entity has what we call an archetype. An archetype is the unique set of components. And we group things together automatically based on that set of archetypes. So now, if we want to remove a component, for example, we want to remove the rigid body component, then we're actually going to move all of the data of this entity into a different chunk, into a different archetype. So now we guarantee that the memory is always laid out linearly, so that the runtime code can process it in the most efficient way. So what does that look like in code? So first of all, you have a struct, you have a movement speed, for example. In this case, we're trying to move an entity upwards. So everything that has a translation component and a movement speed component, we want to move them up. So the move speed component is just a float. And that means, because it's a struct, Unity lays out all of these components automatically for you. So there's essentially one float followed by another float, followed by another float, completely packed linear data. And then in the system, we're saying we want to process everything that has those particular two components. So if we have a movement speed and we have a translation component, then we want to process it. So the system gives us our entities in the order that is optimal for processing them. So we're simply adding a float 3 to the position and we're moving it up. So we're taking the speed by which we want to move it upwards and we're multiplying it by the delta time, and now we're moving the component up. And what's beautiful in this model is that there are really no function calls into the engine that could take time. This is simply processing data. It's changing the data that is there, and it's taking advantage of the inherent layout of the data. Now, this is main-thread code, so it's not, in fact, the most performant way of writing code. Here, you have the same job, same system, using jobified code. Same data, you have the movement speed, but a slightly different way of writing your code. We have to create a job. And in this job, we have a delta time value, which is the time that has passed since the last frame. And we're saying, okay, we want to have an I job for each, with a translation component and a movement speed. Very similar to the previous example. And in our job, we have an execute method, and we're simply moving the component, the position component up. And then below, again, you have the onUpdate method. OnUpdate method gets called every frame. The system gets called every frame in the order that they're defined in the frame. And in this case, we have a rotation job, we assign the delta time, and then we simply schedule the job. And Unity automatically splits up the work into multiple cores. So it distributes all of these iJob for each jobs onto all of these different threads and processes them in the most efficient way. So basically it makes it incredibly easy to just go wide and process all of these components completely in parallel to each other. but it lays out the data in a way that is really efficient. So the thing is, it's different from what you know before with the mono behavior update method and object-oriented code. But it's not significantly harder. It takes a bit of learning of how to do that, but it's safe and it's easy to do. Now, what does all of this mean for content creators? So, we've been working on a different demo that we showed the first time at Unite. And I just want to play that back real quick. Let's take a look. What this demo is really about is it's a stress test for streaming for us. It's a stress test of building a massive world with a small team and showing that Unity is very good at actually streaming a large world with this new system. So let me open that in the editor. So what you can see here, first of all, is that this massive scene, there are 4.5 million separate renderers in the scene. And this massive scene, it loads in the editor in around 4 seconds. And the way that works is that we have a memory-ready data format that we can load into Unity in a really efficient way. Secondly, everything in this demo is in these buildings, right? So you have all these buildings here, and each one is a separate section or a separate subscene. And it can be separately edited, so it makes it very scalable for artists to work because we can simply subdivide our world into all these different parts. And also, while we're working on this scene, the editing representation doesn't always have to be loaded. Usually, it's a really good idea to have only the highly optimized runtime representation in memory in order to actually show what you're editing in context. Right, so if I go here and I select one of these buildings, I can frame it again, and I can click on edit. And what you see now is you have your traditional game objects, your existing scene that works exactly like Unity has always worked. And I can simply select this building here. Move it around. Everything is real time, of course. And I can also go in and see how this building has been built. So we use nested prefabs. Oops, there's not much detail on this one. So you can see here, we use nested prefabs in order to create this. World. So there are all these small pieces that, well, there are these larger pieces that we slap together in a very quick and dirty way, basically, to make that whole level with 4.5 million renderers. Right? Because placing 4.5 million renderers by hand, that would take a very long time. So each piece here is, again, another prefab. So we have this deeply nested hierarchy of prefabs out of which all of this is built. And each air conditioning unit, for example, has 3 separate LED levels. And also, each air conditioning unit has a sound emitter on it. So each sound emitter, there are actually 250,000 sound emitters in the scene, and they compose in real time a dynamic audioscape. And all of that is, of course, possible because we have performance by default. We can just handle these massive amount of components and make that actually work. So you can change these prefabs and thus very quickly build up this massive world. Now, if I close the scene again, and in each of these scenes, we actually have 250,000 renders. That's what is in one of these scenes. And if you want to see how powerful streaming in this new setup is, consider right here. So each building, when we save it, it's really separated into 2 parts. There's the low detail part, which is essentially the shell of a building, and that's maybe 100 separate entities that represent those renderable objects. But then the high detail, we can stream in on top. So just look at how quickly that loads. It's barely noticeable, the difference of just activating or deactivating a game object. But this is loading today. Now, what we're focused on is essentially rebuilding a lot of the engine pieces that you're used to, like a physics engine, an audio engine, a complete rendering engine, AI, visual scripting, all of these things, we're now rebuilding those on top of dots. And so you can use those one by one. Some games require all of them. You can mix and match with the existing game objects. You can put entities and game objects together into the same world. So all of this is something you can try out. The Megacity project folder, you can download it. It's available for download. You can try it out, see how we built it. And I think it's worth checking out, even though it's in preview today, because it's a game changer in the type of content that you can create with Unity. So with that, open for questions.